Szanowni Państwo, chciałbym Państwa bardzo serdecznie powitać na uroczystości wręczenia medalu imienia profesora Włodzimierza Kołosa. Z tego powodu, że część naszych kolegów, naszych pracowników nie mówi jeszcze po polsku, bo mamy sporo gości z zagranicy, pozwolą Państwo, że za chwilę będę mówił po angielsku. I chciałbym jeszcze tylko w tym miejscu zrobić jedną uwagę. My na zaproszeniach nie pisaliśmy, znaczy nie prosiliśmy o potwierdzenie obecności, więc pozwolą Państwo, że nie będę witał licznie przybyłych dostojnych gości, bo mogę kogoś pominąć, no na przykład tutaj panią prorektor, ale więc tylko sobie pozwolę przywitać osoby, które są związane z przyznaniem nagrody. So, good afternoon, ladies and gentlemen. It's my great pleasure to welcome you on the ceremony of presenting the Kołos Medal to Professor Jacek Klinowski from the University of Cambridge. The Kołos Medal is jointly awarded by the Faculty of Chemistry, Faculty of Chemistry, University of Warsaw, and Polish Chemical Society. So first of all, I would like to welcome Professor Izabela Nowacka, the president of the Polish Academy of Chemistry. I will also very warmly welcome the winner of the Kołos Award, Professor Jacek Klinowski from the University of Cambridge. It's a great pleasure to have you here again. We met about 1 year ago. Professor Klinowski is also the laureate of the honorary doctorate of Warsaw University. So to some extent, Professor Klinowski is also a member of our society. I would like to very warmly welcome the representative of the family of Professor Włodzimierz Kołos, astrophysician, Professor Robert Kołos. It's also a great pleasure that you find the time to be present here. The first Kołos Award was given 24 years ago, so it's enough long time to establish some, tradition of carrying out such celebration. So I propose to keep this tradition, and the only difference is that always this award was given at the hall of the Faculty of Chemistry. Unfortunately, now our hall is under reconstruction, so we are at the Biological and Chemical Center of the Warsaw University. As I said, let's make according to the tradition, and we have during this ceremony free speech. First of all, some, of course, only selected achievements of Professor Włodzimierz Kołos is presented, and I asked to do it Professor Grzegorz Hałasiński, and Professor Grzegorz Hałasiński is always the chairman of the award committee. Then I will ask Professor Krzysztof Woźniak also only to present some selected achievements of our laureate. And after that I ask Professor Izabela Nowak to come here and to present the award with me to Professor Jacek Klinowski, and the ceremony is finished by the traditional lecture of the laureate, Professor Jacek Klinowski. So as you see, we have a very rich, program of this ceremony, so I don't want to prolongate it. So Professor Hałasiński, the floor is yours. And I can also give you a microphone if you need it.
Well, I don't know yet. Either this one or this one.
It depends on
I
you,
don't
but
need
I
the
have
microphone.
to.
This is up to you actually to choose.
I
Well,
could
there
get
is this-
an organizer, but I should have to say switch off the second because it works. It not works properly if you have two microphones.
What about that? Do you hear me? Yes, yes, I hear myself, so probably you hear me too. Okay, is my head low enough not to disturb your viewing? Okay. Okay. Somehow. Oh. I'm sorry for the crowded desktop, but let me do a little trick so we could. Anyway, I think I have to find out what this is. This one. Okay, so this is all about Professor Włodzimierz Kołos, 1928-1996, untimely passing away. Probably the best known achievement of Professor Kołos was that he performed first calculations of the dissociation energy of molecular hydrogen with accuracy better than the best experimental determinations of his time. That's not a small feat, actually. This achievement demonstrated the applicability and potential accuracy of quantum mechanics to precisely describe molecular systems. That also means to describe chemistry. In a way, that was this, now young people would call it a game changer. So that was a kind of game changer at the time. And this is why Professor Kołos was widely respected and listened to. Of course, his achievements were plenty, but he was among pioneers of applying programmable computers in chemistry. Before him, actually, this was, well, nobody actually bothered really, and he was one of the pioneers. Next, a connection of quantum chemistry to methodology of theoretical physics. He showed that you can describe chemistry in terms of quantum mechanics. And last not least, he developed theory of intermolecular interactions with short-range forces included. Okay, so let's tell a little bit about his biography. He was born in 1928 in Pinsk, Belarus nowadays, but at that time it was Poland. He received Master of Science degree in chemistry in 1950 at University of Poznań. He undertook graduate studies in theoretical physics under the supervision of famous Leopold Infeld at the University of Warsaw, and he received PhD degree in 1952. It didn't escape my attention that it's only 2 years after his master's degree. Postdoctoral research, which he did in Warsaw after that, was the extension of Thomas Fermi's theory to the problem of electron correlation in organic molecules. So, fairly large molecules for calculations. But then, he, after some time, I'm not sure what year it was, he moved to United States for a postdoctoral research position. He became postdoctoral research associate in Professor Robert Mulliken's laboratory at University of Chicago, USA. As many of you probably know, Robert Mulliken received Nobel Prize in Chemistry for the development of molecular orbital theory. So, right place for Professor Kołos to follow his interests. after returning, in 1962, he joined the Department of Chemistry, University of Warsaw, so the place we are now here. For his research, he received many awards. Some of them I would like to list. In 1967, he became the first recipient of the annual Medal of International Academy of Quantum Molecular Sciences. And 20 years later, he became a member of this academy. Actually, I asked myself why it was so late. But anyway. He became member of Polish Academy of Sciences in 1969. So 2 years after receiving the medal. He was also recipient of several international, or rather, you may say international awards, like Alexander von Humboldt Award, the Medal of Israeli Academy of Sciences, and the Copernicus Medal. Last not least, late in his life, he obtained honorary doctorate from his alma mater, Adam Mickiewicz University of Poznań. He passed away June 3, 1996, and he didn't reach 70 years old of age. So that was untimely death. This is one of pictures of Kołos at Congress of the Polish Academy of Polish Chemical Society in Szczecin in 1977. He gives a lecture. Okay, to sum up, Professor Włodzimierz Kołosa was one of the founders of quantum chemistry. He pioneered in what is now termed ab initio quantum chemistry, computational chemistry that derives only from first principles and provides answers with high accuracy. He advanced understanding of the chemical bond in hydrogen molecule. That was at the time a kind of paradigm, a model for which many details could have been studied. He challenged the experimental measurement and showed that quantum chemistry had to be looked upon as a dependable tool. He was very hardworking and very efficient scientist, precise when communicating with the outside world, also calm and perfect. He appreciated contacts with coworkers and students, and he had great sense of humor while being modest and unassertive. Whatever he did best. And this is a nice picture from Chicago, September 1966, and you can see one of the early, I'm not sure what was it, it must have been some computer already. Looks like a typewriter. I'm pretty sure it is one of the early computers which he used. Professor Kołosa founded a strong research group at University of Warsaw. He did theoretical studies of molecular effects in the beta decay of molecular and solid tritium. He studied muon catalyzed fusion with collaborators from Warsaw and Gainesville, Florida, extremely accurate non-adiabatic calculations accounting for not only Coulombic, but also strong nuclear force interactions between tritium and deuterium nuclei. Well, nowadays it is in fashion to quote how many citations somebody has, and as far as Kołos is concerned, that's more than 10, it's about 10,000. 25 papers were cited over 100 times, 11 papers over 200 times, and 1 paper over 1,000 times. And these seminal papers were about hydrogen molecule, and they were carried out, the calculations and the writing were carried out with Professor Wolniewicz from Toruń and Professor Laureatem from Chicago at that time. These are the 4 records, actually, the first pages. Now to the award, the Kołos Medal. It looks like in this image. This is the picture of it. What about the medal? It is given biannually to commemorate the late Professor Włodzimierz Kołosa, faculty member of the Department of Chemistry, University of Warsaw, and honorary member of the Polish Chemical Society. And both these institutions participate in bestowing this medal. It is given for distinction in theoretical or experimental physical chemistry studies. The laureate presents a lecture at the Department of Chemistry, University of Warsaw, and delivers a scientific talk to the department's graduate students. The lecture we will have today, and tomorrow we will have the lecture for graduate students. The laureate receives a medal, which you have already seen, with his name engraved, a diploma, and an honorarium equivalent to $2,000 US. The laureate is selected by the committee consisting of full professors of theoretical chemistry and physical chemistry from the Faculty of Chemistry, University of Warsaw. The selection must be approved by the Dean of Chemistry Faculty, University of Warsaw, and by the President of the Polish Chemical Society. Both leaders are with us today. The recipients of Kołosa Prize and lecture. You may notice that the first was Roald Hoffmann, and he received this in 1998. So I think we are close to 25 almost anniversary of giving this medal. So maybe this is a good time to remember who invented the medal and lectureship. And that was Professor Bielka, who is today with us in the audience, sitting there, humbly and unassertively. But it was him who invented this. Moreover, he suggested Roald Hoffmann, with whom he spent some time at Cornell University. Am I right? And Roald Hoffmann, not a Nobel Prize receiver. So both things actually met there, really scientific leader, Roald Hoffmann, and also some connection with our students, postdocs. At that time it was Lucian Biela, and later I think Wojciech Grochala went to Roald Hoffmann for his postdoc years. And then when it started, it went on and on, until now, when we have with us Professor Jacek Klinowski, whom we want to reward for his outstanding contribution to NMR spectroscopy. And this is one of nice pictures of Professor Kołosa. And just to warm up a little bit, I added this one. So thank you very much. And I think this is a time for the lecture. Am I right, Mr. Dean? I'm sorry. Of course, I messed up. Yes, so I will get rid of this equipment. And I think Professor Wojciech will... This one...
Probably I do not need any. Maybe
And you don't need any equipment either.
No.
Oh, but we can leave, Professor Kołosa. Which one you prefer? Maybe you would like a more serious one.
Mr. Dean, ladies and gentlemen, eulogy in connection with the award of the Kołosa Medal to Professor Jacek Klinowski. Professor, okay, so I will take it.
Okay. Professor Jacek Klinowski was born on the 11th of October 1943 in Kraków, where he spent his childhood and youth. In 1956, he graduated from the Władysław Jagiełło Primary School and began education at the Bartłomiej Nowodworski High School in Kraków, where in 1960 he obtained his school diploma. He has had an interest in chemistry since he was a child. Between 1960 and 1965, he studied chemistry and mathematics at the Jagiellonian University, where under the supervision of Professor Maciej Leszko, he obtained his master's degree. In April 1968, Jacek Klinowski received a doctorate in chemical sciences from the Jagiellonian University on the basis of the distinguished dissertation, Some Physicochemical Properties of Liquid Ion Exchangers. And soon he started working first at the University of Aberdeen in Scotland, 1968 to 1969, then 1969-1979 at the Imperial College London, where in 1973 he received his second doctorate on the basis of dissertation Theoretical and Experimental Studies of Crystalline Ion Exchangers. He then worked at the Department of Chemistry at the University of Cambridge, where in 1988 he was given the degree of Master of Arts. From 1980 to 2000, Jacek Klinowski went through all levels of scientific career at Cambridge, from Senior Research Associate in 1980-1985, Assistant Director of Research in 1985-1998, and Reader in 1998-2000, to become Doctor of Science in 2000 on the basis of his scientific achievements, then consisting of over 250 publications. From 1998 to 2000, he was also the official fellow and director of studies in chemistry at Peterhouse, the oldest college in Cambridge. In the years 2000-2011, Jacek Klinowski was a professor of chemical physics and a professorial fellow at Peterhouse. In 1998, he was also made a professor by the President of the Republic of Poland. Since 2011, Jacek Klinowski is a distinguished professor at the University of Cambridge, Professor Emeritus, and since 2012, honorary professor of the Jagiellonian University. 1996-2011, he was also a visiting professor at the Adam Mickiewicz University in Poznań, University of Aveiro in Portugal, and the University of Cagliari in Italy. Almost a year ago, on the 8th of December 2021, Professor Klinowski received an honorary doctorate of our university, an occasion which many of us remember very well. An important step in his scientific work of Jacek Klinowski was the position at the Imperial College in London, where he worked under the supervision of Professor Richard Mayling-Barrell, who had created modern zeolite chemistry. Zeolites, crystalline aluminosilicates with an ordered system of micropores synthesized in megaton amounts, are ion exchangers, sorbents, and key catalysts, especially in the oil refining industry. 8 out of 9 catalytic processes in refineries involve zeolites. Jacek Klinowski is one of the pioneers of the method of studying zeolite catalysts using the new, at that time, method of nuclear magnetic resonance spectroscopy with magic angle spinning of the sample, so-called mass NMR. This method has found widespread use in the study of solids. Almost all contemporary publications on the chemistry of zeolites, several thousand such papers are published annually, contain results obtained through the mass NMR technique. Jacek Klinowski is a pioneer in applications of solid-state NMR in studies of phase transitions and the three-dimensional structure of solids. the theory of cross-polarization, applications of reverse cross-polarization, double rotation, mutation of quadruple nuclei, applications of proton NMR in the solid state, or quantitative analysis of difficult to interpret 27 aluminum mass and mass spectra. Professor Klinowski became famous for his in situ NMR experiments, which allowed him to follow the individual stages of the zeolite catalyzed conversion of methanol into a mixture of hydrocarbons forming petrol. These papers, published among others in Nature and JACS, allowed the tracking and understanding of individual stages of the conversion process, their nature and cause inside the catalyst crystal lattice. Numerous works by Professor Klinowski also concern the synthesis and characterization of zeolite molecular sieves with different pore sizes used for the separation of molecules of different sizes and for the catalytic cracking of heavier hydrocarbons fractions. In his work, Professor Klinowski showed the possibility of optimizing both the catalyst and conversion process itself. He obtained sieves with the desired pore size necessary for specific applications, and he examined the structure of many natural and artificial silicates. Truly pioneering. Their properties, cations of such elements as gallium, vanadium, or titanium, as well as works devoted to explanation of the mechanism of channel formation in such systems. Professor Klinowski also studied various minerals, carbon, especially its new allotropic forms at that time, fullerenes, wood and ceramic, biological and other materials. The work of Professor Klinowski is truly interdisciplinary. For example, NMR studies of mineralized brain tissue of people suffering from Alzheimer's disease showed for the first time the presence of aluminium in the human nervous system. It should be mentioned that Professor Klinowski undertook the first spectroscopic studies of inorganic pathological deposits in living organisms, as well as studies of toxic radicals generated by aluminosilicates. Research carried out by Professor Klinowski also concerned fullerenes and their complexes, the structure of graphite oxide, which is used as an electrode in lithium batteries and in membranes and composite materials. After the award of the Nobel Prize for Graphene in 2010, these papers have been cited thousands of times, one more than 3,600, and the other one more than 1,700 times. It is worth mentioning that work of Professor Klinowski on the synthesis and characterization of new metal-organic coordination frameworks, important for applications for gas storage, photoluminescent, magnetic, optical, catalytic, and photochromic properties. Several of these papers are cited more than 500 times each. Professor Klinowski is an authority in the field of solid-state and nuclear magnetic resonance. The list of his publications includes 502 items, which had a huge impact on the scientific community. More than a dozen publications appears in the most prestigious journals in the world, such as Nature, 10 papers, Science, or Lancet. 51 papers by Professor Klinowski have more than 100 citations, two have over 1,000. The total number of citations is bigger than 20,000, while the Hirsch index reached an impressive 69, one of the highest ever achieved by scientists of Polish heritage. He's also the co-author with Professor Jacek Klinowski of 2 monographs on NMR spectroscopy and editor of 3 other books. The important position of Professor Klinowski among scientists dealing with mass NMR spectroscopy is shown by the fact that for 20 years, until 2011, he was the editor-in-chief of the scientific journal Solid-State Nuclear Magnetic Resonance. Another object of interest to Professor Klinowski is mathematics, which he studied years ago at the Jagiellonian University in parallel with chemistry. He's published 23 papers on applied mathematics devoted to such issues as global minimization, minimal surfaces in physics and chemistry, number theory, Riemann zeta functions, or continuum fractions. One of the most interesting results in this area allows enumeration using timing theory all possible hypothetical types of structures for 1, 2, and n component systems. And I'm sure we'll learn more today from the lecture of Jacek. This revealed many new types of structures and elegantly summarized all available knowledge about possible crystal structures. The structures obtained can be checked for their chemical and structural sense, especially those having large free spaces, voids, or channels, in which important chemical reactions can be performed with the aid of catalytically active functional groups. The work of Professor Klinowski contributed to the synthesis of many important structures envisaged by such theoretical considerations. Many detailed problems in science, natural science, technology, economics, electronics, and logistics require finding the global minimum of the functions of many variables. This global minimization optimization is one of the most universal research problems in modern world, and at the same time, one of the most complex, due to the need to find a global minimum in the presence of a large number of ubiquitous local minima. In this field, Professor Klinowski also made his mark by publishing papers devoted to a new global minimization algorithm called taboo search. In subsequent papers, Professor Klinowski showed that the use of taboo search leads to a global minimum and introduced a practical method of global optimization. These methods are now widely used in predicting macromolecular structures and researching the mechanisms of neurodegenerative diseases such as Alzheimer's or mad cow disease. The study using the Monte Carlo method, for research on the spread of HIV and AIDS in Africa is also very impressive. 35 years ago, it was discovered that there had been a Shakespearean theater in Gdańsk. Although William Shakespeare himself has never visited Poland, actors from his company performed here. A foundation, Centrum was created with a view of rebuilding the theater. The patrons were then Prince of Wales, now the King Charles, and Andrzej Wajda. The theater opened in 2015. Jacek Klinowski is a member of the Board of Trustees of the charity organization British Friends of the Gdańsk Theatre, who support this foundation. Professor Klinowski's interesting film is worth mentioning, as shown by his co-authorship of a multi-volume book which first appeared in the United States as Cinema, the Magic Vehicle, and in Polish as Kino, Wehikuł Magiczny. The English version is still available from Amazon.com as an e-book. Professor Klinowski has greatly contributed to the education of scientific staff. He has promoted more than 27 doctors. He himself probably is not that sure how many of them. 8 of whom are now rectors, and 3 others, prorectors of their universities. The association of Professor Klinowski with Poland is very strong. For 30 years, he's been a foreign member of the Polish Academy of Arts and Sciences, an honorary member of the Polish Chemical Society and the Polish Zoolite Society. For many years, while a professor at the University of Cambridge, he also lectured the PhD students at the Faculty of Chemistry of the Jagiellonian University on NMR spectroscopy. Young academics from the Jagiellonian University and other Polish universities, including our University of Warsaw, did research internships in Cambridge under the supervision of Professor Klinowski and participated in joint research projects. Out of 502 publications by Professor Klinowski, several dozen have our Polish colleagues as co-authors. Jacek, one of the scientific leaders of the Faculty of Chemistry at the University of Cambridge, is known for his excellent lectures. He amazes with the importance of his achievements, versatile interest and interdisciplinary approach, an excellent example of the creative possibilities for a man who participates in international science at the highest level. I would like to strongly emphasize the extraordinary kindness and hospitality of Professor Klinowski and his wife Margaret, who is in the audience, who have supported numerous groups of young and experienced researchers from Poland and wider world. Every year, many people visited their house in Cambridge or their flat in London, always receiving help and hospitality. The scientific achievements and the life of Professor Klinowski, a true Renaissance man, a scientist of world class and achievement, a long-standing ambassador for scientific cooperation around the world as well as the scientific world in Poland, a scientist who has left his mark in so many fields, a long-time friend of Polish scientists, fully justified granting Professor Klinowski the Kołosa Medal. On this very special occasion of awarding the Kołosa Medal of the University of Warsaw and the Polish Chemical Society, I wish you, Jacek, health and further success in both your scientific and numerous non-scientific activities. Congratulations and thank you very much for your attention.
We decided that I will take the heavier part, and Professor Novak the more convenient one. So may I ask Professor Klinowski to present you the award and the medal.
Yes. Książka Polskie Towarzystwo Chemiczne jest zlokalizowane w miejscu, w którym Polska się urodziła, czyli na Wrocław. Tak, to zapraszamy przy okazji na Wrocław.
To jest medal z drugiej strony.
Tak.
Staram go się nie upuścić.
Nie uciekł.
Jest bardzo. Cała przyjemność po naszej stronie, panie profesorze. Zapraszamy. The floor is yours.
Mr. Chairman, Madam Vice President of the University of Warsaw, Madam President of Polish Chemical Society, the award which I just received was a tremendous honor for me. I have to I knew Professor Kołosa personally. I knew he was a great scientist. I knew he was cheated out of the Nobel Prize, but I didn't know how prestigious the Kołosa Medal was until my colleagues explained to me. One of my colleagues said, look, how many Olympic gold medals are there? Thousands. And how many people got the Kołosa Medal? 10, 11, including yourself. Well, this is an exaggeration, of course, but you understand what he was trying to say. Now, let's go down. These are my collaborators, and this is that I finally understood what Koło's medal is when I received 2 days ago this message from one of the laureates, Professor Joachim Zauer from University of Berlin, Helmholtz University in Berlin, who sent me this message. Congratulations for the Koło's medal. Among the honors I received, this is the closest to my heart. And this comes from a man who has lots of honors and is a member of 4 academies. I mean, I know of 4 academies, maybe more. So he is a scientist of world class. Well, I couldn't repeat this to you without permission, so I'm asking him for permission to repeat it. And he says, dear Jacek, say, sure, and say hello to my friends in Warsaw, Włodzimierza Kołosa and Grzegorz which I have already done, Mr. Chairman. Well, I am in a slightly embarrassing situation because I only learned 10 minutes ago for what I received the Koło's medal. I didn't know the citation for NMR spectroscopy. And we work on various things. If I knew that, I would have spoken about NMR spectroscopy, which I'm going to talk about tomorrow to students. But my formal lecture is about something quite different, and I hope interesting. If you allow me to say a few words about my university, which I forgot to mention last year. Well, this is the aerial view of Cambridge, a city of 130,000 inhabitants. These are the courtyards of colleges. This is Trinity College, Cambridge, in which Isaac Newton lived in these rooms here near the entrance, and these are the other colleges. The system is very, very strange. The system is dual. There are colleges under separate administration, individual administration, and there is the university. You can study any subject at any college. There are 30 colleges. But of course, every college cannot have an observatory for the astronomers, chemical lab for the chemists, and so on. So they meet in university institutes, which are quite separate. And most people work in both colleges and universities. But the college, the director of studies for a given student is located in the college. Now, this is my college, Peterhouse. Now, a lot of great of this world came through this door. Madame Curie-Skłodowska and her husband, Albert Einstein, crowned heads, and so on and so on, famous scientists, famous pianists, and so on. This is why it's very interesting to be a member of a college, because you meet people whom you would never meet in ordinary life. But then Cambridge is not ordinary. All right? Now, we have in our library the first edition of Copernicus, De Revolutionibus Orbium Celestium, but I think the most interesting thing is this. You see, this threshold has been there for since 1270 and is worn out by millions and millions of feet. Now, what is 2 meters under this threshold is even more interesting. An enormous cellar with thousands and thousands of bottles of fantastic French wine. I know exactly how many, but I'm not allowed to tell you. Where is the switch? Ah, I have to. Not true. No, back. Back. Ah, I have to show you this. It is said, often said, that disasters always come in pairs. And in the year 2000, our university and the whole country were touched by two disasters: Brexit and COVID-19. Now, you may wonder what this is. This is King's College Chapel, the most photographed place in Cambridge, our best known building. Now, in front of this was a lawn which was mown twice a week for 800 years until COVID came. During the war, it was still, bombs were falling down. The first bomb that hit England, it hit cinema in Cambridge actually. But the lawn was still being mown. But during COVID, it wasn't. So in the end, the grass grew like this, and they had to bring horses. Okay?
So this is the picture of now.
Okay. This is a picture taken last year. Last year. But it could have been taken 500 years ago, of course. It is so strange. Now, the subject of my talk is enumeration of possible new structures. Let me start with an observation that always struck me. The enormous amount of shape and form, variety of shape and form in the physical world. Now, this is a book that everybody knows. It lists minerals and natural and synthetic substances and various strange structures that occur in them. Now, there are, of course, lots of types of plants, and the similar situation applies to living forms. Now, you would think that there is nothing special in this little beetle, except that it's 40 centimeters long, and it's really quite nasty. It's one of millions of Brazilian insects. It has its name, Latin name, Lupus ferrodentus cavallero. Lupus ferrodentus in English, a wolf with iron teeth, and cavallero is the name of the discoverer. Now, the same happens under the sea. Look at this. This is a 19th century drawing of small objects, small living organisms in the sea. And this one is Angel of the Deep. This is a strange animal that lives 3 kilometers under the surface of the Pacific. Now, I cannot tell you why it is colored, since it lives in absolute darkness. So my main interest is the reason for this complexity everywhere, including in chemistry. Now, why do these things exist? Well, they exist because they can, okay? And they can because the rules leading to their creation are very simple. And I will show you what I mean. What is this? This is a 19th century book by Darcy Thompson on growth and form. He describes various organisms. He describes the sunflowers, for example. The seeds in the head of a sunflower are distributed according to the Fibonacci series, and he's the man who noticed this, and so on and so on. And he so tells you what kind of helix we are dealing with here. It's a disaster. No. Well, to tell you how very simple rules can lead to very complicated results, I will first describe to you the Mandelbrot fractal. Benoit Mandelbrot was a French scientist who was actually born in Warsaw and emigrated as a child. And what Mandelbrot fractals does, you put a point on a two-dimensional surface, which has certain coordinates. You square these coordinates and add a certain number, always constant number c, and you have a new number. And then you square the coordinates of this, add c, and you have a new number. Well, very simple. You just square the previous one and you get the next one. And what you get is very, very strange. Of course, the colors are artificial, but there is black and white, basically. Now, this is a very strange object of enormous complexity. Let's imagine that I take a part of it, a little square somewhere, and enlarge it 10,000 times. What do I get? I get the same. You see these strange objects appear here, and they appear there forever. It's infinitely complex, this fractal. Mandelbrot himself had no idea what it looked like because he could not calculate sufficient points. He knew that it was something very, very odd, but could not calculate the sufficient number of points. Now, Lorentz oscillator is another example of complexity. Look at this. There is a point in space, and there are three equations describing how it should move with time. This is the change of the x coordinate, this is the y coordinate, and this is the z coordinate. Now note that they are not separate because x appears also in the equation for y. They are not separate. And there are three variables which you can adjust. And depending on the value of these variables, the point goes wherever you like. It can go around the sphere and so on and so on and so on. Note also that here the value of beta is 8 divided by 3. It's not 2.666. Computer doesn't accept 8 divided by 3. It accepts 2.66666. Now why am I saying this? Because this point, with these values given here, behaves rather strangely. It goes round the spiral, as you can see, and then suddenly jumps out of the spiral and continues along a different spiral. Why is that? Because of the accuracy with which this value of beta is given determines its path. You see? The value of the initial conditions is essential for this. And I'm telling you about this because these are the equations used for predicting weather. the results that you hear on television depend on how well the simulation was done, and this means how well the initial conditions were given. Now, I'll tell you a story from real life. In 1994, the man who forecast weather on British television, on the BBC, was called Michael Fish. And Michael Fish comes in front of the cameras and says, tomorrow, wiatry słabe lub umiarkowane. Oh, of course he says it in English. But what he said was quite wrong. The next day, we had the greatest hurricane for 200 years, causing enormous damage. Now, Michael Fish was, of course, finished because he couldn't appear on television anymore because he was a object of ridicule, even though he did nothing wrong. It's the meteorologists who told him wrong, and they were guilty because they didn't put the initial values with sufficient accuracy. Anyway, now look at this very strange thing. Wolfram Rule 110. This is very simple. I have an infinite chessboard, all white. There are only white fields, and I put a black point. This is the first generation, black point. Now, this is this point here at the top. This black point, this is the first generation. Now, what comes in the second generation, which is this? It depends on the neighborhood of the black point. And I'm giving it a rule. I can give it any rule I like, but I like this one. So, you see, if it's surrounded by two other black ones, it dies from overcrowding and produces this. Okay? If it has different neighbors, it produces black. Anyway, applying this rule on and on and on, okay, always examining what is in the last generation, you obtain this this is after 256 iterations. Now, Rule 110 has a strange property because it's Turing complete. It can simulate any algorithm at all, calculation or computer program. Everything is there. If you just do it for long enough, it will be there. And this is a very rare property. I hope you know all about who Alan Turing was. Alan Turing was a mathematician from Cambridge, of course, who during the war was taken to work on the decoding of German messages. There was a special unit. We know, of course, that Polish scientists were absolutely key to this. But after the Germans added one wheel to the enigma, the matter became impossible. Now, this is all described in a film which is called The Imitation Game. It won an Oscar. Polish title is Gra tajemnic. It tells you about Turing. Now, British establishment treated Turing disgracefully, but nobody knew that because what he did during the war was a total secrecy. Until about 20 years ago. They kept it a secret for 50 years. So this man, during the 30s, wrote the most important paper about computing ever. And computer did not yet exist, remember. And during the war, he won the one of the Atlantic. Okay, it came to light 20 years ago. And since then, he is a national hero, and his portrait is on £50 note. Okay? Now, final example of complexity is this. This is probably the most famous paper of the 20th century, DNA. It's not that many people actually read it, but it is the 430 words and a rather primitive drawing done by the wife of one of the authors. And the punchline is in this sentence: it has not escaped our attention that. And then he says that he knows how it works as a genetic material for multiplication of genes. Now this is a beautifully written paper, very English, modest but triumphant. Very nice. Well, what about DNA? You may say this is a very complicated material. Indeed it is. But it works because there is one rule. There are 4 amino acids, and we know 23 simple amino acids, but nature only uses these 4. T, A, C, and G. Thymine, adenine, cytosine, guanine. Okay? And A always goes to T. You see, A always goes to T. And G always goes to C. You see? So, why is it a spiral for a start? Because the bond lengths are such that it has to wind up. But what's the secret of it? If you split it along its length, the half has the same information as the whole. Because if, sorry, no. Because it knows that A has to go to T and G has to go to C. So half of it is as clever as the whole thing. And this is how, of course, genetics works, that one half from the father, one half from the mother, and so on. So basically, the rule of operation of this, I'm not a biologist, so I'm only carefully saying only things which I do understand. Now, let's ask ourselves a general question. How many different structures are possible in organic, say, chemical structures? Why do I want to know that? You see, it's not enough to say that something is not known, to study it, because we know very little about the physical world. We can't study everything, and we don't know very much. So it has to be an important problem. And the reason I have is that if I imagine and justify some new structure, I may be able to make it if I think it can be of use. And also, if I have a library of all the possible structures, I can, without having them, I can generate X-ray diffraction patterns, and if something new is found, I can say that whether this thing already exists. You see, it will give you the structure. But I'm not interested in just anything. I'm interested in these substances. Imagine a square like this with silicon atoms at the corners, and oxygens halfway through sides. So there are no silicon-silicon bonds, but these are silicon-oxygen-silicon bonds. As oh God. Well, I dare not touch this because, you know, it's very strange. Now, this square can combine further to build these cubes, and objects like this in the middle is a cage which fills space by itself, very rare property, and double membered rings. And you have structures like zeolite A and forgesite. Zeolite A does not occur in nature, but is produced in megaton quantities. Why? Because it's used for separating oxygen from nitrogen. The openings in the channels are the size of small molecule, and it preferentially absorbs oxygen. Now, it's also used in washing powder and such things. And on the right, you have forgesite, which is a very, very rare mineral, but it's also manufactured on megaton scale, because it is a catalyst in the production of oil and many other things.
That sound is dreadful.
Sound is dreadful.
Got scared.
Anyway, now, you saw these structures before. If from time to time you introduce an aluminium atom by replacing silicon, aluminium has different valency than silicon. Therefore, by introducing an aluminium atom, you are turning the whole framework into an anion. It has an electric charge. So it has to have a cation to counterbalance this. Now, this cation can be anything, can be sodium, normally in nature it's sodium. But if it's hydrogen, it turns this powder into very, very strong solid acid. Thousands of times stronger than sulfuric acid, but you can still hold it in your hand. But if a visiting organic molecule enters the channel, the hydrogen jumps on it and plays havoc with it, converts it into something quite different. So this statement, 28% of world's petrol was created at this desk. This is Dr. Weiss's desk at Laureatem in America. And he discovered that zeolite Y was a cracking catalyst. Cracking means splitting large molecules, because oil is something, large molecules, rather unpleasant. If you cut them into pieces, you can get petrol and other things. Now, what is petrol? It's 5 to 10 hydrocarbon without oxygen, 5 to 10 carbon atoms. Now, under the microscope, you can see that these channels are a reality. Okay? This is my colleague Bob Woodward, not Bob Woodward, Bob Freeman did this photograph, and you can see that there are channels. They are 12 and 0.3 angstroms apart. So they are very narrow, but small molecules can enter. Let's do a little calculation. Let's take a cube of this material, 1 centimeter side. Now, how many, and let's look at the front wall. How many channels are there in this direction? There are 8.13 angstroms apart. So 8 million, 8.1 million in this direction. And from top to bottom, also 8 million. So how many are there together? 6 times 10, 10 to the 13th. 10 to the 13th. But remember that there are also channels going from right to left and from top to bottom. So there are 3 systems of channels. So let's multiply this by 3. And you got a number which converted into kilometers, because each of the channels is 1 centimeter long. If you convert it into centimeters, you get 2 billion kilometers. in one cube of this strange material. Now, what is the distance from here to the Sun? 148 million kilometers. So in this cube, there are channels which are 13 times longer than the distance from Earth to the Sun. As T.S. Eliot, the poet, said, I will show you fear in a handful of dust. Ja wam pokażę grozę w garstce prochu. And this is a situation which fits this lie. All right. This is another very strange molecular sieve. It is the most complicated, structurally, the most complicated inorganic solid we know. It has a chemical formula of SiO2, silica, krzemionka, but it has 24 inequivalent sites for silicon. It is fantastically complicated. Okay? And it also has very interesting properties, discovered accidentally by two American researchers. They were passing vapor of methanol through this WSM5, and they got petrol from it. This is the artist's impression, you see, and this is the molecule of methanol, which is not a valuable chemical at all. And neither is ethanol. The government puts $32,000 on a cubic meter of ethanol, but this it has nothing to do with its real value. As a chemical, it's nothing. It's just a few dollars. It is almost feasible to use this if oil becomes a little bit more expensive. So in countries like New Zealand, where there is no oil, it will become possible to produce petrol by this. You can see here that you have molecule of water and molecule of hydrocarbon. Now, this hydrocarbon, of course, doesn't mix with water, so you can see two layers which you just separate. Okay, so this is quite a useful material. I think you would agree with this. Well, following this paper of ours, which is one of the best known papers we have done, quite a long time ago now, every possible 3D network can be enumerated. And I will tell you how we have done this. This is a cover in Nature of which we are very proud. In how many ways can two-dimensional space, I'm not talking about 2 dimensions, I'm talking about tiling a floor, for example. In how many ways I can do this? With 1, 2, or 3 kinds of tiles, so the tiling is periodic. In 2 dimensions, there are 11 ways. Result which was already known to Joachim Kepler, who was the great astronomer, and also a very clever chap. So he also knew this in the 17th century. And 508 and 16,774 types of binodal and trinodal, meaning with 2 kinds of inequivalent and 3 kinds of inequivalent. Now, he couldn't possibly calculate this. This is our result. So we said 11. So these are the first 3. You can see clearly that all the nodes are identical. And these are the remaining 11. And that's it. There are no further possibilities. Now these are scribblings from his notebook. Now, we cannot deal with something like this. This is the Penrose tiling. Everybody in this room knows that you cannot have 5-fold symmetry.
crystal with fivefold overall symmetry. You can have local symmetry, for which Sheckman already received the Nobel Prize, a very interesting material. And in 2 dimensions, you have the Penrose tiling. Now, Sir Roger Penrose, the greatest living British physicist, is a Dr. Honoris Causa of this university. We cannot deal with this. It doesn't have a unit cell. You can see at a glance that it's regular, but it does not have a unit cell. I'm hopeless with this material. Now, imagine this is the only part of my lecture which requires attention, but only for 2 or 3 minutes. Imagine that you have 2 kinds of tiles. You have an octagon, okay, red, and a square, blue. In how many ways can I tile the floor using these 2? This is not an easy problem. Oh no, this is a very difficult problem. How do we deal with this? I have to divide both these original tiles into squares. What is the simplest way of subdividing the plane? The triangle. It's a simplex. It's in 2 dimensions. Simplex in 2 dimensions is 3 points not lying in the same line. So a triangle, in other words. A simplex in 3 dimensions is 4 points, tetrahedron not lying on the same plane. Okay? So I'm showing you a 2-dimensional argument which we later applied to a much more complicated 3-dimensional problem. But how did we do this? Now you can see I am putting a solid line around the original tiles. You can see that. Then I'm running a dashed line from the center. This is the so-called barycentric division from the center of gravity to the half of the side, a dashed line. And I run a dotted line to the corner. Okay? You can see there are dashed, solid, and dotted lines. Now you can see that some of these triangles are similar, are the same. Okay? This A is the same as this A, and so on and so on. In the end, there are 6 kinds of tiles, 6 kinds of triangles. And what I showed you on the picture is listed on this. Tau A comes from an octagon and is connected with the dashed line with tau B, with the dotted line with tau B, and so on and so on and so on. Now, you can put it even more simply. From this, you can recreate the original picture. Now, you can do it like that. This describes the first kind of triangles. It is connected with triangle B through a solid line, with triangle B with the dashed line, and triangle B with the dotted line, and so on and so on. So you have 6 inorganic gene. We call it, we just came to our head, we call it inorganic gene. Now, to get all possible structures, all you need to do is to use a permutation of these 6. Now, how many permutations of 6 objects are there? 6, exclamation mark, 6 power, 6 silnia, 720. And that's it. So we know that from this actual arrangement, you can do 720. I'm particularly interested in 4 connected networks, which I showed before, such as silicates, aluminosilicates, and so on. They occur in Then we know about 320 minerals, and half of them, more than half of them, are silicates. And this is because silicon, oxygen, and aluminium are the lightest elements. They came to the surface to the Earth's crust. This is why vanadates are somewhere down and light elements are here. So I'm interested in enumerating the 4 connected networks. Now, I do this, of course, in 3-dimensional space using tetrahedra instead of triangles. If I use try to explain to you how it works in 3 dimensions, it would be almost impossible to visualize, how space is filled through tetrahedra. Never mind that, I promise you we did this correctly. There is something called, how do we recognize the structures we know? There is something called the coordination sequence. You start with this atom at the center, and it has 5 first-order numbers, first-order neighbors, 11 second-order neighbors, 16 third-order neighbors, and so on and so on. And this series is almost unique to a given structure. It's not absolutely unique. It can happen that you can put different structures with the same sequence, but it's very rare. And we then examine this personally. So computer recognizes a known structure straight away. Now, what I have been telling you about obtaining structures is not chemistry, because these are topological objects. They are not chemicals. So let's make them into chemicals. Let's put the corners silicon. Let's make everything SiO2 of different structure and calculate the energy, because the things with the lowest energy with respect to alpha quartz, which is the lowest energy in silica, is the most likely. So what do we get? So we see here all the known molecular sieves listed. This is the crystal energy, and this is the density, framework density, number of silicon atoms per 1,000 cubic angstroms, you see. These outlying points are not on the straight line because they involve other elements, so zinc and so on and so on. We're not interested in that. We're interested in those here. So we know that whatever we create is likely to have physical and chemical sense if it lies in a certain area. Say something like that. You see near this line, it cannot be too dense and it cannot be too open. And it has to have framework energy within a certain range. So look at this. We find that there are 14 uninodal, 14 binodal, and 147 trinodal structures which fulfill this criteria, and you can see them here. This is the area of interest, of chemical interest, because it's all of topological interest, but this is of chemical interest, and this is the magnification. These things you can make, okay? Some of them have been, since we published our papers. 59 hypothetical structures have been synthesized as our enumeration was published. Now let's, for example, on an obscure conference, somebody produced a structure and a diffraction pattern of this material, and we can see that this is this structure that we had predicted, which wasn't then known. You see, it's Ampere. Look at this strangeness with arrangement of channels like propeller in a submarine. Okay? And look at this with flat channels, so it can separate flat molecules with globular molecules, you see. This is the idea. And look at this one, which has 3 kinds of channels in different dimensions. This is the so-called realistic volume of the framework. And this is really curious. It has 16 membered channels, and the channels outlined by 16 silicon atoms. And this has never been found, and it involves 93% empty space. But that is just perfectly feasible. There is a saying, nature abhors a vacuum, but I think this only applies to dentistry, not to chemistry, and perhaps to politics, of course. So, our results apply to various classes of structures. We have actually stopped this because I think that the most important thing for a scientist is to know when to start working on something, and even more important, when to stop. But since we have published the way to do this, anyone can enumerate structures. I'm not interested in details. I'm working on something quite different. So this is all I have to say. I would just like to thank my dear wife, Jacek Klinowski, for supporting me. Without her, I would not have the Kołosa or anything else. Thank you.
Thank you very much, Professor Klinowski, for this fascinating talk and this, how to say, very wise comment. That it's very important to know when you should stop the project and find something more interesting. So the lecture is open for discussion. Maybe somebody want to ask a question? If no, I have one question. Could you say what is the efficiency of production gasoline using this zeolite? It means 100%. It's quite a quick process. Yeah, of course.
You can, of course, run a car on methanol, but you shouldn't, and I tell you why. Because this molecule has a molecular weight of 33, of which 16 is oxygen. It doesn't do anything. So you're carrying it in your tank, which takes volume and weighs further, but a hydrocarbon is burnt completely 100%. So this is why it is of such interest to remove oxygen.
Microphone, please.
Microphone.
Thank you.
Okay?
Yes,
Is it
excellent.
better?
Thank you.
Okay.
So maybe somebody else would like to ask a question. If not, so thank you very much for this fascinating talk, and we are really very happy that you are the next laureate of the Kołosa Award. So it's a really very great pleasure for us to see you
I
again.
just wish I would talk to you about nuclear magnetic resonance, for which I received the prize. But there you are.
Yeah, so, but you have also talk tomorrow, so I see that there are some specialists in NMR spectroscopy, and they will, how to say, thank you second talk. So thank you very much, and the ceremony is ended. So thank you.